As promised, we've arrived at prisms. Let's get started. In this section, we're going to start our journey into prisms. We're going to go over the basics of a prism. We're also going to talk about different ways that we can define a prism, deviation power, also apex angle and deviation angle, and then finishing up with prism thickness. So first off, we want to talk about what does a prism do to light and how does it affect the image that we view through a prism, right? So let's look in the text. So the most important thing for you guys to remember about prisms is the last line in this first paragraph, right? When light enters a prism, right, it's going to be deviated towards the base, right? And that's going to cause the image to shift towards the apex, right? So we want to highlight that. You want to put a star right there because that's really important now, right? Now, question to you is which one of the eyes going to follow, right? Do the eyes follow light or are they going to follow the image? Yeah, that's exactly right. Eyes are going to follow the image, right? So you could also write out to the side, eyes are going to follow the apex. Very good. Now let's get into 4 different ways that we can talk about defining prism. So let's take it to the whiteboard. So let's talk about 4 ways that we can define prism. This is going to help us break down prism into some areas that we can focus on and help us study in our board's preparation, right? So the first way that we're going to talk about ways to define a prism is going to be deviation power. How much is light going to be deviated because it goes through a prism? Second way we're going to talk about is going to be apex angle and deviation angle and how they interact with each other, correlate to each other. The third way we're going to talk about defining a prism is going to be based on thickness, and that's just going to be the simple fact that the base of a prism is going to be thicker than the apex of a prism, and we'll talk about that and how to use that in a problem. And then the fourth way we're going to talk about prism is going to be decentration and Prentice's rule. So on this video, we're going to go through 1, 2, and 3. We're going to leave number 4 to our next 2 videos because we're going to spend quite a bit of time going through decentration and Prentice's rule because there's a lot of clinical applications for both of those. So the first way that we're going to talk about ways to define a prism is going to be deviation power, right? And so whenever we talk about deviation power, it's going to be this concept that if we had light going into a prism, right, light would continue on all the way to a screen if the prism wasn't there. But like as we talked about before, because light going through a prism is going to be deviated towards the base, it's going to leave at an angle. It's going to be different as it goes towards the screen, right? And so we can define the power of a prism as how far, right, is the light going to be deviated in centimeters, right, over how far away a screen is from the prism in meters. So whenever you look in your text, you'll see this equation, prism power equals, and we use a y because it's vertical over x, right? And you want to keep in mind that with the amount that light is going to be shifted on a screen, that's going to be in centimeters, right? And the distance from the screen to the prism is going to be in meters. So this is going to make prisms number 2 in terms of our equations, right? So number 2 in terms of our equations that does not use meters exclusively, right? Do you guys remember what number 1 was? Yeah, it's exactly right. Minimum blank size, right? Minimum blank size uses everything in millimeters, right? So now that we're in prism land, we're going to do everything that we're going to use in prisms is going to not use meters exclusively. So we're going to elaborate more on this whenever we get to the live lecture, but that's going to be one way that prism can be defined. It's going to be deviation power. So now let's talk about the second way we're going to talk about defining prisms, and that's going to be apex angle and deviation angle. So you can draw this on the same picture that you already drew, or if you would like, you can pause the video and draw this again on the page where apex angle and deviation are in your text. So apex angle is going to be the actual angle on the prism, right? That's going to be your apex angle. The deviation angle is going to be the angle here. That's going to be the angle that light is going to be deviated because it's going to be shifted towards the base of the prism. Now, you're not going to have to worry too much about sine, cosine, and tangent aspects of apex angle and deviation angle, but there is going to be one equation that I want you guys to know. It's in your text, right? It's going to be deviation angle equals, right, your apex angle times n minus 1, where that n is going to be the n value of your prism, right? Now, I stole this from a student. They gave this to me a couple years ago while I was lecturing, and I loved it. I think it's a really easy way to be able to remember that, is remember this as the Dan minus 1 equation, right? So deviation equals apex times n minus 1. Just remember it as the Dan minus 1 equation. Very, very good. So that's going to be apex angle and deviation angle. Let's keep on moving on. We're going to talk about prism thickness. The third way that we're going to talk about prisms is going to be prism power, and prism thickness, okay? So the main concept here, we're gonna kind of draw a picture. So think of this as like looking at a pair of glasses, right? So here's gonna be our patient, right? Okay, so here's their patient eyeball. It's like we're looking at the patient from above, okay? So this is their pair of glasses. Here's gonna be our temporal edge of the glasses, right? Here's gonna be our nasal edge of the glasses, all right? So we're looking down over the patient's head, looking at them from above, all right? And because of the temporal edge of their glasses is thicker than the nasal edge, right? They're gonna have some prism that's gonna be induced in their glasses, all right? Now there's a specific equation that we're going to use for calculating this prism thickness. So let's go over that. That's going to be in your text. So equation 5.30 says the prism is going to be equal to 100 times G times N minus 1 over L. All right. Now the G is just going to be simply the difference in your thickness, right, between your base and then your apex. All right. So just a simple difference in thickness between the base and the apex. Now the L value is going to be the length between your base and your apex. So it's kind of like the length of the pair of glasses or the length of the prism. Both of these are going to be in the same unit. So you want to circle that in your text, right? So right there in the middle of your text, you guys see L is the apex to base length, same units as G, okay? And that's the key point as we're going through here. It doesn't matter whether you use centimeters, millimeters, or meters. You just have to make sure that both of them are in their same units for this equation to work. Now, when are we going to ever do this in clinic? We're not really ever going to do this in clinic. The only reason we go over it now is because it makes for a decently good optics type question. So let's go through the example, and I think that'll help kind of illustrate this point, help it understand it, kind of hammer it home. So let's go through example 5.13. Find the prism at the center of the following lens minus 6 diopters with an index of 1.523. Assume the lens has an A dimension of 50, a B dimension of 30, a nasal thickness of 4, and a temporal thickness of 6. So why don't you take a second, pause the video, that way you can work the problem, and then we'll come back together and work it. All right, so let's talk about how we solve this problem. So the first thing we're going to look at is trying to figure out what is our G value, right? So we said the temporal edge was going to be 6 millimeters, right? The nasal edge is going to be 4. So 6 minus 4 is going to give us 2 millimeters. Is going to be that difference in thickness between the base and the apex in this pair of glasses, right? Our A dimension is going to be 50 millimeters, right? We're talking about horizontal prism, right? So we're talking about a nasal and temporal edge. So we're going to use our A dimension, right, as our length of our prism. Now, if we were using superior and inferior thickness, right, then we would use our B dimension for this base to apex length. But in this case, we're doing horizontal, so 50 millimeters, and then our index of 1.523. So whenever we plug that into our equation, right, we get an answer of 2.1 diopters as the power of prism that's going to be induced only because the temporal edge is thicker than the nasal edge. Now the question I have for you to kind of finish this thought, right, is that what type of prism is going to be induced? Is it going to be base out or base in prism? That's exactly right. It's going to be base out prism, right? And why is that? Because the base direction is out. It's going to be temporal. The temporal edge is thicker than the nasal edge. You're going to get base out prism. Now, what would happen if instead of having 6 as our temporal edge, right, we had 4, right? And our nasal edge would 4. What kind of prism would be induced based on thickness? Yeah, that's exactly right. There would be a big fat goose egg, right? Because the only reason that we have prism in this example is because the temporal edge is 6, which is going to be thicker than our nasal edge. Awesome. Like I said, guys, this is not an equation you're going to use all the time. It's definitely not something you're going to do in clinic, but I want you guys to see it so that way if you see it on a quiz question, smart test, whenever it comes up, you're going to be able to dominate it as we move forward. You guys are doing great. Keep up the good work, dominate the quiz, and I'll see you on the next video.